Hello, class. In this module, we're going to cover charging systems. Okay. Now, the main component of the charging system is the alternator. I want to say main because the battery is part of the charging system in a sense, because the battery is where all the electricity that is generated from the alternator is stored. Okay. But the alternator is the main component of the charging system. Okay. Alternator, well, the thing the alternator does is it creates electricity. So it generates electricity. Some manufacturers do call it a generator, which is fine. We can call it a generator or we can call it an alternator, but alternator is a more common word at this point. They used to be called generators, and on modern electric vehicles, the generator and the motor are the same thing. So generator, alternator, you can use them interchangeably, but most of the time, if you go to, like, say, to a parts store, you ask for the alternator, you don't ask for the generator. Okay. A couple things to note about it here. The the housing, the outside of it is made of aluminum. Now, if we know anything about aluminum, I'll ask you a question. Is aluminum magnetic? Can we connect a magnet to aluminum? The answer is no, we cannot. So the way an alternator works is it creates electricity through electromagnetism. And the reason we want the outside of the housing of the alternator to be non-magnetic is so that electricity and magnetism isn't generated within the housing. We want to be able to touch the housing or mount things to the housing without having electricity or magnetism generated in the housing. Okay. And that's the main reason. So non-magnetic, lightweight, aluminum is lightweight, much lighter than steel, iron, but obviously it's non-magnetic, and that's more important than it being lightweight. Okay. The last thing, heat transfer. Aluminum, because it's a lighter metal, can dissipate heat faster than, say, steel or iron. And so that's the other reason we use aluminum, is to dissipate heat quicker, because heat is generated within the alternator, and we don't want the heat. We don't want the alternator to heat up too much. Okay. So how does this work? So if we think back to when we talked about electromagnetism, it works in the same exact principles, meaning we are going to hold one conductor and we're going to turn another conductor. So we have two pieces of metal that can be close to each other. They don't touch. They could have coils in them, meaning windings of wire and copper wire within each of those pieces of metal. We hold them really close together, and then we spin one of them and we hold one of them. Okay, so one stays still. We usually put them within inside. We don't put them next to each other in a sense. We're like left and right. We usually put them within each other. So there's a rotor that is within a stator, and that's how the alternator works. So meaning that we're going to put a rotor within the alternator, so it's surrounded by it, kind of like a donut. And then within the center of the donut is the rotor, and we spin the inside of it. So in a 360-degree circle on all sides, so to say, the rotor is getting in contact with the stator through electromagnetism. So it's really, really close to it at all times. And then we spin it. The way we spin it is through the engine. So the engine is actually going to spin it. Okay, that's why the alternator is actually connected to the engine through a belt, usually a serpentine belt. Okay, so again, we're going to spin the rotor, which is the inner part of, say, the donut, and then the outer part is the stator, and they both have metal windings in them. They're both made of metal, and they both have wires within them, but we spin one and we hold one, and then we generate electricity that way. Now, well, what type of electricity is generated in there? I hope everyone knows that, but alternating current is generated in there. Okay. And if we want to increase the amount of electricity we are getting from the alternator, we increase the speed of it, meaning your alternator will produce more electricity at a higher RPM. So if you're just sitting there idling at the stoplight or stop sign, you're producing so much. If you want a little bit more, and then you got to rev up the engine or just drive the car. As you drive on the freeway and your RPMs go up, you increase the amount of electricity. We can get more conductors, meaning we'll have more wires in there, get bigger pieces of metal and more windings within the alternator, but that's going to come from engineering. We physically can't do that. We can control the speed of the conductor, but we can't control how many number of conductors are within it already, because that's done already from the factory or made that way. and then increase the strength of the magnetic field. So same way we can either, that's a combination of the two. We can either get more conductors or we can increase the speed either way. And that'll increase in turn the magnetic field, which will increase the electricity, the amount of electricity that's created within the alternator. Okay, so the alternator sometimes does have a slip ring on the end of it in the rear section. Sometimes some of the newer ones, I don't want to get too in depth into some of this stuff because some of this stuff is more how it's made. For us as technicians, and if we're just trying to look at the alternator and determine if it's good or bad, it should be relatively easy. Is it outputting the amount of voltage that we want it to output to the battery? That's really what we're going to be looking at, determine if it's good or bad. We no longer rebuild alternators, we just replace them. You take it out, you take it to the parts store, they give you a new one. You leave your old one with them as a core charge, so you don't get charged for the core. And then you put the new one in, and that's it. We don't, we're not worried about the internals of it in a sense of what actually went bad. We can, it's good to know. It's nice to understand, so we understand how they work. But in diagnosing and repairing, we don't go that in depth in it. Okay. So some of this stuff you can go ahead and read and write it down. Anything that's highlighted, make sure you write down for the quiz. Um, some of the alternators they're only meant to turn one direction. Okay. Again, if we're creating an alternating current form here because alternators produce alternating current, which means it's AC. Now we only want it to go one way because if it goes backwards, it can go the opposite way into the battery, meaning that the electricity can go through the negative instead of the positive in some ways. And we don't want that to happen. Okay, so some alternators do have a one-way clutch, meaning it'll only allow it to turn one way. Okay. On some of these are just showing some special tools if we wanted to be able to change the size or change the pulley size, I should say. Now, on some alternators, I'm gonna go back just one. Um, you can see here on the right side here with this picture. Let me circle it for you. That's the pulley. Okay, so here's the belt. So the belt goes down. So the belt turns the pulley. If we wanted to change the size of that pulley, we could. Now, why would we want to do that? Now, if we wanted to change it to a smaller size, by changing the pulley to a smaller size, what does that do? That actually speeds up the alternator. So by speeding up the alternator, that's one of the ways we can increase the amount of electricity. So we can get the alternator to produce a little bit more. In theory, alternators could produce 100 volts, over 100 volts easily. Okay. But the thing is, our vehicles only work off 12 volts. We don't want to produce that many volts. We don't want to produce 100. We can produce, say, 13, 14, 15. I would say even maybe a little above 15 would be okay, but we got to be careful. Once we start getting above 15.5 and into 16, that's an overcharged condition. We don't want to charge it too much. We want to charge it just enough, but not too much. If we try to charge a battery at 20 volts, we're going to cook the battery and we're going to mess up our electrical system because our electrical system is only rated and it really should only be used for roughly around 12 to 15 volts within that range. Okay. And so that's what this tool here is showing. It's just there are ways to change the pulley if we would want to. Now I talked about these two parts a little bit, but the rotor is the portion that's the picture up here in the top or upper right here. This is the rotor that I just circled. Now the rotor is what creates the magnetic field, but also that's the part on the inside of the alternator that is turning. That's the portion that is connected to the pulley, which is connected to the belt, which is connected to the engine. Okay, that's the portion that turns, and that is within the donut, so to say, the donut looking thing, which is the stator here on the bottom, which I just circled right now. So the stator is the one that is on this, that's the stationary portion of it, and it is on the outside. So that's where the electrical current is produced. Okay, so the magnetic field is really produced in the rotor. The stator is where the current, the electrical output is produced. Okay, the stator does not turn. That's the stationary portion, and the rotor is the rotating portion. That's the portion that turns within the stator. Okay. Now this is just a picture just to show how they're kind of mounted together. It shows how the stator is around on the outside. So let me highlight or let me draw. So up here is the stator. There's a cutaway so we can see the inside, and down here is the stator. So the stator is in a circle. It's on the outside, and the rotor is in the middle, and that's the portion that turns. We can see the pulley over here to the right. Okay, so the pulley's on the right. That's what's turning the rotor within the alternator, and the stator on the outside. That's where the electricity is generated. Okay, and that's just a cutaway, so we can kind of see what's going on the inside of it. The there are slip rings. So these are the slip rings over here on the right, the red and the green items over here on the right. This is where a positive and negative are produced, or we get it from when we check an alternator. And this is within the actual alternator within the rotor as it's spinning around. Okay, we're not really going to check these because we can't get access to them while the alternator is turning. What we're going to check is the output voltage on the alternator. These would be positive and negative, which is AC, alternating current. Okay, again, we can't really check these. We're not going to check them in a sense because we're going to check the output voltage of the alternator. Okay, again, make sure you write things down that are here. So that way, if you find a question on the quiz, it could be easier for you to answer instead of going back and looking things up all the time. Okay. And this is just a blowout picture, exploded view, so to say, of an alternator. So we have our pulley, which is the first portion, which is the first part right there, which I just drew an arrow to. Then we have the casing, some bearings, right? Then we have the rotor. Then we have the stator, and those are the main two components of the alternator. The rotor goes within the stator. The one thing we are going to talk about in a second is the regulator and the diodes. Okay, then you have the back housing. But the regulator and the diodes, those are very important too, because the regulator is what regulates our voltage. Earlier, I said that the voltage could reach up to 100 volts plus if we wanted to, if it's capable, the alternator is capable of doing that. But we never want it to do that because we will fry our electrical system in our car. So what we want is we want the regulator to regulate the voltage, meaning to keep it somewhere around 13 and a half to 15, somewhere within that range. That's what we want the regulator to do. We don't want to let it to go too high. The diodes, so a diode is a unit. I'm going to draw the symbol for a diode. Okay, so there's a diode. A diode is an electronic component that only allows electricity to go one way. Okay, now the alternator produces, like I said, alternating current, but our batteries, they work off of DC current. Our vehicles work off of DC. So we have to change AC to DC current. That's what we have to do. Alternator produces AC. Our vehicle uses DC. So the way to do that is we send AC current through a diode. Okay. The diode it only allows it to go one direction. So AC goes above, it goes positive, negative. So I'm going to draw it down here at the bottom. So it's 0, and then we have plus, and we have minus. So AC is like this. It goes above, below 0. But when we change it and we send it through a diode, so if we send it through a diode, all of a sudden, draw a diode right here, then it goes only positive and goes to DC. You notice how the path changed a little bit there. Okay. So that's the purpose of the diode. Okay. And there are 3 diodes because there's 3 wires within the stator. The three-phase electrical, 3-phase stator, 3-phase alternator. So that's what we're looking at here, down here in this picture below, that I drew down here. Okay. We had the diode changes AC to DC in order to charge the battery, because that's what our vehicles run off of. Okay, and again, this I drew it on the last picture because I didn't want to I didn't have enough space here to draw it. So the diodes again change AC to DC, and this was what we're looking at here. That there, it's nothing to look at. It's just these tiny little electrical components. They're really small, and they're put within this rectifier bridge, or diode trio, sometimes they call them. Okay, and there's these fins here that help dissipate a lot of the heat. Okay, but this is what one would look like. This is what like a diode trio would look like. if you were to take it out of the alternator. Obviously, we're not going to do that. That's not something we do anymore, but just so you can visualize, see what they look like. Okay. I think we've talked about this before, but if not, the field current can be computer controlled, meaning how do we limit the amount of voltage, the amount of current going to the battery, and how much current the alternator needs to produce to be able to charge the battery? That can be computer controlled. Okay, so we can adjust it through the computer. Everything is computer controlled nowadays. There are sensors on the battery, on the cable, on the alternator itself, and connected to the regulator. And those connectors and those sensors, the signals go back to the ECM or PCM, and they can be computer controlled. The computer can determine, do we need a little bit more voltage right now, or do we need less voltage right now? Depends on what the vehicle needs. Okay. There are brushes. Sorry, brushes are located in alternators. They're also located in starters and any other electrical motors, but the brushes are there to get the electricity out of something that is rotating back to where it needs to go. So the brushes are spring loaded. And if you notice up here in the upper left picture, okay, the upper left picture, the brushes make contact with the slip rings. Now, because these slip rings are spinning and electricity and magnetism is being created, we want to get this magnetism out of electricity out of the spinning portion of it and into the stator and back into the regulator, through the diodes into the regulator and back to the battery, right? Well, we have to get electricity out and magnetism out. So but out of something that is moving. So the way we do it is we have to have contact with it at all times while it's moving. And these brushes here, what they're called, they're spring loaded. They push up against the turning, spinning rotor and slip rings. Okay. Now these wear down is what happens. So over time, these start to wear down because they're constantly spinning and spinning and touching the spinning portion of it. And eventually over time they will wear down to the point where they have to be replaced, or you just replace the alternator at that point. They do last a long time though. On new alternators, an alternator nowadays should last 100,000 miles on most vehicles, I would say, if not more, 150,000 miles at this point before it goes out. Okay. So we do have a lot of time with them before these brushes and other components in the alternator start to wear down. Make sure you're writing these things down that are highlighted in yellow so that it'll help you with the quiz. Okay. Now, what we're looking at was what I drew earlier. So this is a sine wave. So a sine wave is an alternating current diagram, so to say, or how we graph alternating current. So again, you'll notice the 0 is right in the middle. Okay, there's our 0 line right straight through the middle. Then we have a positive and negative. We're not putting exactly how much voltage because it changes, but we know it's positive and negative. Now, as of right now, there's only one line. Okay, one, that's it. Make sure you write down what's up top too as well. We go to the next one. Now there's 3. Okay, why is there 3? Well, if we go all the way back to the original picture, one of the original ones, sorry, now it's too far back, where there it is, where the stator is, you'll notice we have 1, 2, 3. 1, 2, 3. Okay, we have 3 wires coming out of the stator. Okay, it's a pair of wires actually. We want to think of it that way, but we have 3 connections coming out of the stator. Okay, now let's go back to where we were. Now here, each line represents one of those connections. Since there's 3 of them, and there's 3 lines here, this is called a 3-phase alternating current. Now, all of our alternators and all of our vehicles are 3 phases. It uses 3 separate windings to be able to create electricity. Okay, why do we use 3? Because it's more powerful, because we can generate more. The key about them though is that they're all wired within a circle, right? And a circle is 360 degrees. Now, each phase is, if we take 360 and we divide it by 3, that'll give us 120, meaning that each phase is 120 degrees away from the next one. So 120 degrees, one is going, then the next 120 degrees, another one, then the next 120 degrees, then is another one. Okay. The reason they do that is to reduce the amount of interference and the amount the amount of, say, magnetic interference, meaning they're not fighting against each other. So these three phases are working independently of each other, in conjunction with each other, and not pushing back against each other as much. Okay. If they were closer together, so if we had all three phases in only 5 degrees apart, so to say, it would be very unbalanced. So the alternator would shake in a sense, because all of the force, all the magnetic field to be created within, say, a 10-degree, 15-degree rotation out of 360 degrees. So you'd have a lot of magnetism, a lot of electricity being generated, and then none for a while, and then it starts again, and it's like a jolt. So if we phase them out, we make them more even, only they're all 120 degrees apart from each other, then it's smoother in a sense. And then that way they're not fighting against each other, and all the phases can work independently and help each other to be able to charge the battery quickly and efficiently. Okay. And this is how the diodes are laid out. So we have 6 diodes, 1, 2, 3, 4, 5, and 6. So there are 6 diodes right there. If you follow the path, they are all connected to each phase. So we have one phase. We'll just say this is phase 1, this is phase 2, and this is phase 3. Okay. That's a weird looking 3, but you get the point. So we have one phase here going across, going around. Okay. Goes to ground, and we have 2 diodes for this one phase. Okay. So that's for phase 1. Phase 2, we go over here. This is for phase 2, those 2. And then these 2 down here are for phase 3. Okay. So again, we have 2 diodes for each phase. The reason we have it is because, remember, we're dealing with alternating current, and there's a power and a ground on each side. So we want to put enough of the diodes to be there to be able to control the ground side and the power side. So here, this way it goes. We have a right side and we have a left side, so to say, in this diagram. But it's power and ground. So we want to be able to control the power and the ground. We want to make sure the electricity only goes one way, which is back to the alternator. Okay. Back to the battery, sorry. So that way, all these go that way. Okay, so I hope that makes sense to everyone. Again, if you need to, take your time, look at the picture, pause the video, or go back to the original PowerPoint. And this is a different style. So this other one was a delta, I think it was. And then we have a Y winding. Yeah, here's a delta. Sorry, the first one was a Y, and this is a delta. So there's just different styles, different ways to wire it. You can see the windings and how they are within the stator, and the differences between them. It's more visual than anything. Okay. Understanding which one you have in your car is not really that important, to be honest with you. It's not going to change anything. We're just going to test it the same. It's going to work the same, and you may never know what type of alternator you have in your car. If you're interested in looking more in depth, then you are welcome to do so. But this class wouldn't cover that. That'd be more of an engineering type of class of the benefits of delta over Y or Y over delta. Okay. Last couple things here. So this just as a point here, it's a a note, something to take note of. If you ever have a bad alternator and the alternator is bad, it's been tested bad, you should not continue to drive the vehicle. You should replace the alternator as quickly as you can. Okay. The reason is that the alternator, specifically the stator within the alternator, can damage the battery. Okay, can cause more harm, or a bad battery can cause a bad stator. So I should say the opposite way too. If you have a bad battery in the vehicle, the battery's bad, it's been tested bad, don't keep driving the car, replace the battery. Okay. You can cause damage to the electrical system either way. So if we have a bad alternator, replace the alternator. If you have a bad battery, replace the battery. Don't keep pushing these things along. Kind of like if you have a flat tire, you have to replace it right away, or you have to fix it right away. You can't keep driving the car. Same thing with a bad alternator or bad battery. We shouldn't be driving it. Okay. If you have a bad sunroof, who cares? Close the sunroof and it's no big deal. Just don't use it, right? That's not a big deal. But these are things that need to make these components make the car go, and they make the car work properly. So they have to be replaced and kept up to date when we find a bad component. Our typical voltage regulator range is roughly within this range, within 14.2 to 14.6. The minimum I've seen that is still good is around 13.5 volts to around 15 volts. Okay, so 13.5 to 15. The regulator may want to keep it within this range, keep it roughly around 14.4 maybe. okay, as an average. But as low as 13.5 and as up as high as 15. And I've even seen a little bit above 15 and still be, usable, doable, and workable. Okay. And the last couple slides here, a voltage regulator can control current. I think we already talked about this, but the voltage regulator is going to be computer controlled on modern vehicles, and the computer is going to control the regulator and what the regulator can do, and it's going to adjust the voltage up or down as needed. Okay, that's why it can go as low as 13.5, as high as 15. This is more of an older vehicle. This picture that we're looking at here is more on older vehicles, coolant connections. I haven't seen any newer vehicles that have coolant connections on the alternator. I'm not saying it doesn't exist. You may or may not see it, but it's not common at all. Okay, we don't really have coolant connections on alternators anymore. Not really needed. Much like the starter motor on most vehicles, alternators, as they turn into hybrid vehicles, they're going to go away. So on a hybrid vehicle, we actually don't have an alternator or a starter. We don't need one because we have a hybrid electric motor within the transmission that starts the vehicle and that charges the battery. So we don't need it anymore. So eventually, if most or all vehicles start moving to hybrid, and I've seen more and more hybrids that become available, the alternator and starter will eventually go away and will not be needed anymore. Okay. A current sensor. If you ever see this black component that is around the negative battery cable, that is a current sensor, meaning that the current is being sensed on how much current is going back to the battery. The computer needs to know this because the computer needs to know this because it needs to know how to regulate it. Is it enough? Is it not enough? To increase it, to decrease it, okay, to allow more current, to allow less current. So there's a current sensor on most vehicles, and usually it's on the negative cable. It's not always on the positive cable. In this instance that we're looking at, I'm not sure what kind of vehicle this is, but it is showing it on the positive cable, but it could be on the negative cable as well. And what it looks like a black ring that's around the one of the cables. Okay, it doesn't touch it, but it's just around it. Okay, so don't remove it if you ever see it. Okay, and this is the last one. I'm gonna stop here. There is one more slide, but that slide is a video, and the video is actually on Canvas already. If you want to go back and watch the video, you can. It's within where the PowerPoint is. Now, the last thing I just want to show you real quick is our DC signal here. So if we're going to measure voltage at the actual alternator or the battery, meaning the bolt on the back of the alternator or at the battery on the battery post, we would get a DC signal. Okay. And then we would have our on and off time, how much is on and how much is off. That's if we would use a graphing meter or an oscilloscope to be able to get this graph. But we are going to be checking DC current. Okay. Even though an alternator produces AC current, when we check it, we're checking DC current. And that's the signal, the symbol that we're going to look for is this type of signal here, this straight line signal, because it's not AC. AC would be the wave pattern. Okay. So again, go ahead and go through the PowerPoint and look at the other video that is available for you on this topic. If you have any questions, reach out to me. And as always, thank you very much for your time.